In the year 1178, on a summer evening in June, 5 monks stood outside a cathedral in Canterbury, England, and saw something impossible. A crescent moon hung in the sky. As they watched, the upper horn of the crescent, the tip pointing toward the stars, seemed to split open. A flame shot out of it. Sparks scattered. The moon writhed, in the words of one of the monks, like a wounded snake. And then it went dark. They wrote it down. Carefully, 5 witnesses, describing something that shouldn't have been possible. And for the next 800 years, nobody knew what they saw. The moon is the most familiar object in the night sky. It may also be one of the least understood. In 1976, an American geologist named Jack Hartung proposed an answer. He suggested the monks had witnessed a massive meteorite impact on the moon, one violent enough to throw glowing debris into space, visible from Earth. He even pointed to a candidate, a relatively young-looking crater called Giordano Bruno. For a while, that seemed to explain it, except it didn't. An impact that bright should have filled Earth's skies with meteor activity in the following days or weeks. There's no record of that. Later studies suggest the crater may be much older, and the physics of producing a visible flash at that distance still isn't fully settled, so we don't really know what the monks saw. And that turns out not to be an isolated mystery. Because the more closely we study the real moon, not the simplified version we carry around in our heads, the more we find a pattern. Not one mystery. A pattern of them. I want to show you what I mean. Start with something that feels obvious. The moon is just there. A stable companion orbiting Earth unchanged on human timescales. That's not quite true. The moon is drifting away from us. Right now, about 3.8 centimeters per year. We know this because Apollo astronauts left mirrors on the surface, and we've been bouncing lasers off them ever since. The timing is precise enough to measure the distance changing in real time. It's slow, but it adds up. 100 million years from now, the moon will sit thousands of kilometers farther away, far enough that total solar eclipses, the kind where the moon perfectly covers the sun, will no longer happen. We exist in a narrow window where the sizes line up just right. The moon is 400 times smaller than the sun and 400 times closer. That's why the disk fits exactly. That ratio isn't required by physics, it's timing. A coincidence of when we happen to be here. Every generation before us has seen it. No generation eventually will. Eclipses feel permanent. They're actually temporary. The moon isn't just drifting, it's shrinking. As its interior cools, the moon is contracting, losing roughly 50 meters of diameter over the last few 100 million years. Not much on a planetary scale, but enough to matter. Because the crust doesn't shrink gracefully, it cracks. Long cliffs called thrust faults run across the surface, some of them stretching for kilometers. Some are geologically young enough that they're likely still active. Some appear to be associated with moonquakes. And here's the limitation. The only continuous seismic data we have comes from instruments Apollo astronauts left behind, which were turned off in 1977. We have strong evidence the moon is still seismically active. We just haven't measured it directly in nearly 50 years. And when we did measure it, lunar quakes behave differently from ours. On Earth, a magnitude 5 quake lasts seconds. On the moon, similar events can last for nearly an hour. The whole body resonates, like a bell that doesn't damp easily. You could start watching a full episode of television when one began and still be feeling it in the closing credits. Some of these quakes are linked to tidal forces or temperature changes. Others, particularly the shallow, stronger ones, don't have a confirmed trigger. We've recorded them. We understand parts of them, but not all of them. We have measurements without mechanisms. That pattern continues. The moon has an atmosphere, technically an exosphere, so thin that atoms rarely collide with each other. But it's real. Trace elements: helium, argon, sodium, potassium, constantly replenished by solar wind and micrometeorite impacts. And that exosphere forms a tail. Sunlight pushes sodium atoms away from the sun, creating a faint stream that extends hundreds of thousands of kilometers into space. Once a month at new moon, that stream sweeps past Earth. The moon has a comet-like tail, and once a month, Earth passes through it. We didn't discover this until 1998. Even now, the exact balance of processes sustaining that sodium isn't fully constrained. Micrometeorites likely play a major role, but the observed distribution is still being refined. The moon is more active than it appears. Quiet doesn't mean inactive. It means we're not noticing yet. And it's more asymmetric than it should be. The near side, the face we see, is covered in dark volcanic plains. The far side is almost entirely different. Thicker crust, far fewer maria, and a much older, more heavily cratered surface. We have models that explain parts of this, but not a single explanation that resolves all of it cleanly. One hypothesis proposed in 2011 suggests that early in its history, the moon merged with a smaller companion moon. A slow, low-velocity collision that pancaked extra crust onto one side. It's called the Big Splat, and it's still being debated. The face we've been staring at for our entire species' existence might be the scar of that collision. Or it might not. We don't know yet. Which leads to the bigger origin story. The moon formed from the debris of a collision between early Earth and a Mars-sized body called Theia. That's the leading model. It explains the composition. It explains the orbit. It explains the system as a whole. But it also raises questions. In 2023, researchers proposed that two massive structures deep in Earth's mantle, continent-scale regions known as large, low-velocity provinces, might be remnants of Theia itself. Not scattered debris, not chemically absorbed material. Actual chunks of another planet, still partially distinct, still down there. That claim is not proven. It's not directly testable with current technology. We can't drill to them. We can't sample them. But it's plausible enough to be taken seriously by the people who study this for a living. And if it's right, then Earth and Moon aren't just neighbors. They're the outcome of a shared, violent origin. Material from two worlds, fused into one, with pieces of the other still preserved inside us. That's what the moon is. That's what we are. The moon isn't just orbiting Earth. It's part of what Earth became. And even after all that, the surprises continue. The moon was once thought to be completely dry. It isn't. Water ice exists in permanently shadowed craters near the poles, places where sunlight has never touched the surface, where temperatures sit close to absolute zero, where ice has likely been accumulating for billions of years. We've confirmed it directly. There are also trace amounts of water across the broader surface, likely formed through interactions between solar wind and lunar minerals. That process is still being actively studied. The exact mechanism by which surface water forms, migrates, and persists isn't fully settled. We understand the presence of water. We're still refining how it works. And then there's the surface itself. Lunar dust is not like Earth dust. Under a microscope, it looks like broken glass. Microscopic shards, formed by billions of years of micrometeorite impacts, fusing and shattering the regolith over and over again. It's sharp, it's jagged, it's electrostatically charged. It clings to everything. Apollo astronauts brought it inside their landers on their suits, and it caused problems immediately. Buzz Aldrin said it smelled like spent gunpowder. Harrison Schmitt developed what he called lunar hay fever within hours of contact. Sneezing, congestion, watery eyes, a reaction to inhaling material that had never been weathered by air or water. And the dust behaves in ways we don't fully model. Near the boundary between lunar day and night, the terminator, dust particles appear to levitate. Photographs from Apollo 17 show a faint glow along the horizon at sunrise, believed to be sunlight scattering off airborne particles that shouldn't be airborne on a body with no atmosphere to speak of. We think it has to do with electrostatic charging. We haven't proven it. The moon doesn't just sit there, it reacts. So at this point, step back and look at the pattern. A moon that is slowly drifting away. A surface that is still shifting and cracking. Quakes with partially understood origins, a tenuous atmosphere forming a planetary scale tail, a two-faced structure we don't fully explain, evidence of a violent origin that may still be detectable deep inside Earth, water in places it wasn't expected, dust behaving in ways we can't completely model, not one mystery. A pattern of them. I want to stop here for a second and be honest with you. Most of what I've told you so far has a partial explanation. Scientists are working on it. The gaps are real, but they're the kind of gaps that get closed as instruments improve and data sets grow. This isn't ignorance. It's unfinished knowledge. What comes next is different. For centuries, observers, professional astronomers, amateur astronomers, monks in cathedrals have reported brief flashes, glows, and color changes on the moon's surface. Short-lived, localized. Sometimes lasting seconds, sometimes minutes. Astronomers call them transient lunar phenomena. Many of them almost certainly have ordinary explanations. Small meteorite impacts, gas release from beneath the surface, optical effects from Earth's atmosphere. Some have been directly confirmed as impact flashes by automated telescopes, particularly in the last decade, but not all of them have been matched to a specific mechanism. There are catalogued observations of the crater Aristarchus glowing red. There are reports from the Apollo 11 crew in orbit describing a brightening in the same region, a report that Houston, at the time, asked them to double-check. There are decades of consistent cross-referenced sightings from independent observers that don't map neatly to any single known cause. Modern monitoring has confirmed that short-lived events do occur on the moon. Not exotic, not supernatural, but not always fully explained either. Which brings us back to the beginning. The monks in Canterbury saw something in 1178. We can propose explanations. We can test some of them. We can rule others out. But we can't close the case. And that's the part that matters. The moon is one of the most observed objects in human history. We've studied it for centuries. We've visited it. We've brought pieces of it home. We've mapped its surface at resolutions finer than most of Earth's ocean floor. And still, when we look closely, we keep finding places where our understanding runs out. Not because the moon is breaking the rules, but because we haven't finished learning them yet. 12 people have walked on its surface, all of them in a narrow band near the equator. On the near side, more than 50 years ago. We haven't been to the far side. We haven't explored the poles in person. We haven't stood inside those permanently shadowed craters where the ice has been waiting. We haven't directly measured its seismic activity in nearly half a century. We've only seen a fraction of what's there, and even that fraction keeps surprising us. The moon isn't a solved object. It's a familiar one. And those aren't the same thing. Familiarity is not the same as understanding. The monks saw something we still can't fully explain. Modern instruments are seeing things we're still working to understand, and every time we look closer, the pattern holds. The closer we look, the less finished the story feels. The moon is still keeping secret.